right, so we've learned about what event systems are, at least in principle, and what they're trying to do. And now we'll talk a little bit more about how they actually work in practice. So how event systems work. All right. So it's actually not very hard. As a programmer, the first thing you do is you need to set up what are called callbacks or listeners. And this is just like interrupts, okay? Maybe many of them, for example, are actually at the start of program. If you're unfamiliar with this, a callback, a listener, it's a fancy word for a function. That's it. It's a function. It's a function. And you start it up that if this event happens, call that function, okay? That's all that you do. So you can imagine it might look like something like this. Register a keyboard. Or register on keyboard, sorry. I'll erase that. Register on keyboard. Right? If a keyboard event happens, you give it a function. You say, okay, call that function, keyboard pressed or whatever. And you say, oh, well, I'm also curious about the mouse. So you register on mouse event. You can call a function. And if you get into this, it's not just graphics and interactive. There's networks, there's timers, there's all kinds of stuff that you can subscribe to or set up callbacks for. But once you're done that at the start of your program, you leave it behind, you forget about it. And then you run your central event loop. So you set up your callback at the start of your program, you do all of your initialization, you get a graphics context, you set up your window, blah, 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 blah. Okay. Other events, by the way, window resized, window shrunk, window closed, all kinds of them you can set up. Once it's done, then we have this central event loop, and it looks something like this. While, not end of program. So basically it goes forever until there's some signal that the program is over, the person clicks the X or something. What it does is it gets events. So E equals get next. It's an X. Get next event. So if an event came in, it was processed, it was put into our data structure, it was put on the queue, remember? Put on the queue in order, and then it returns it. If there's no events, this sleeps until the event happens. Again, operating systems concepts, right? It can sleep until an event comes in. It doesn't waste time checking, are you there yet? Are you there yet? Are you there yet? It sleeps, event comes in, it wakes up. Or it just gets them continuously as long as there are events there. So I get this event, what do I do with it? We dispatch it. Okay, based on the type. So basically, this calls your function. Maybe nothing if no one's listening. It just throws it away. No big deal, right? So this is usually a list. Many people can be listening, but we've already done that, right? We've already solved that. So when you register to listen, you could add it, let's say, to an array list of listeners. All these functions add up, and then when an event comes in, you go, you get it, you get it, you get it, you get it, you get it. And we won't get into the details of whether something consumes an event or whether it propagates to the next one. That's not really the point of this. But I just wanted to mention that because there are little nuances in there. But the main point you should realize is that your main program is just this really simple loop that gets an event in the order it came in and sends it to your callback function. Now, I said earlier that this is a single thread, and it is a single thread. So what happens here is just a regular loop. If I'm going to call this dispatch here, I'm going to highlight underneath here. If I'm going to call this here, as you know from basic programming, it can't continue to the next event until that function returns, right? I'm going to call your function. We set it up that way. A mouse event came in. It calls your function. Cool. Well, I can't get the next event until you return. It's just as basic programming, right? I call your function. I'm waiting for the return. That's how it works. So because it's a single thread, we can't go to the next event until the first one returns. So because this is a single thread, one event handler must finish before the other starts. Before another can run. Okay, this actually is really important to realize. Even in processing, even in the Windows systems that I'm familiar with anyway, there's single-threaded event handlers. And that's important because then it guarantees that order of queuing that we've talked about, right? That's what we want. But because it's single-threaded, if you have an event listener that does a lot of work right in there, it's going to slow down the whole program. You need to keep your event handlers short. Quick, I should say. Okay, keep them quick, because if you're doing a lot of work in there, you're slowing down. No other events can go, and no other events can get handled, okay? So keep your event handlers short, and I said this verbally, but this guarantees order of processing. So I mentioned this earlier. It's really important that you realize why the order of interrupts matter and why it's important we keep this single thread to have that order of processing our events. Imagine, here's an example I cooked up. Mouse move. You push the shift key and then you click. In this case here, if you process the click before the mouse moved to the button, then you click. But if you process the click before the mouse move, you might have thought you missed the button when you actually hit the button. So the order changes the outcome. In fact, you'll notice it becomes quickly meaningless if we don't know the order. When you have mouse move, mouse click, shift, key press, all of these things. The order is crucial, okay? So really important to keep that queue going in order. How these things work and actually how you implement them, it's mostly syntax, but it's language dependent. So event system implementation is language dependent. So for example, if you're doing C, you can do it with function pointers. I've done a lot of this. Despite the ugly syntax of function pointers, it actually becomes very liberating once you've solved this in C. It's very easy. In Java, they're called listeners. And then C#, they're called delegates. It's the idea of passing a function as a variable, as a parameter, because that's what a callback does, right? I'm like, hey, call this function. But it's not solved necessarily at compile time. I pass it the function name. It has to save a pointer to where that is in memory, so to call your function later. If you've never worked with listeners or delegates, that's a really weird idea. Where wait, I can pass a function name to as a variable, and then it can call that later. Yeah. Okay. So if you're not familiar with that, I really don't want to go into too much detail, but look up Java listeners, Java C# delegates. It's a really not a bad idea. You can just pass functions as information. You also do it the object-oriented programming way, which is what happens in Java and C#. But you're passing an object, and they call a known function within that object. You get the same effect. But anyways, I really did not mean to get into this stuff. The cool thing about this is because these are syntaxes built into a language, you can extend them and make your own. When I did a lot of robot programming, this was really useful, right? Robot stopped, robot started, you ask it to process some computer vision thing. it's done. When's it done? Events is a great way of signaling all these asynchronous processes that you don't know how long they'll take or when they'll happen. So it's really cool. I really like this stuff. Now, the other thing I'll mention is earlier we kind of did talk about interrupts versus polling, but that's not really how it works. These days, your event system encapsulates a polling device, right? So you'll have some code somewhere that's really tight. It does polling if you need to, if the device demands it, but you wrap that into an event. If it changes, you generate an event. So the event systems, they can encapsulate a polling device and generate interrupt-like behavior. So you don't have to poll. The polling's still under the hood. It's still happening if it's required for that device. But it's a tight loop, and its only job is to check what it needs to in the efficient way and generate the interrupt. So you still get all the benefits of the event system, where I can handle it whenever I want to, handle them in the order that the events came in. Okay. So now's a good spot to take a break. We'll come back and we'll learn a bit more about how to use them. This is how they work, and now we're going to start talking about how do we actually use these event systems.